packet, the handout? Okay. This is our last lesson for this lesson, I guess you could say. So I think we briefly filled out the top of this page yesterday, and now we are going to go ahead and finish up those examples at the bottom. And I did actually answer the first question, I think, for a couple of those, but I did not answer like all that the question was asking. So I want to revisit these problems anyway. Okay, so the instructions, remember, said find the vertical asymptotes in the holes of each rational function. Also, describe the behavior of the graph on each side of each asymptote and hole. Okay, so I think we answered the first part of that question, but not the second. So we're just going to start over completely on that. Okay, so the first thing we do is we factor the top and bottom, in this case just the bottom, and you'll notice that nothing cancels out. You factor the denominator and nothing cancels out, so you can see that x equals -2 and x equals +2 are vertical asymptotes. Okay, nothing cancels out. There are no holes in this problem. No holes. Okay, so now it's time to analyze the behavior of the graph on both sides of each asymptote. That's 4 limits, folks. We have to calculate 4 different limits. We're going to be calculating the left and right limit at 2 and at -2. So we need lots of space for this. You'll just have to write small, sorry. So the first thing I'm going to do is do LIM x goes to -2 from the left. And then we'll do LIM x goes to -2 from the right. And then we'll repeat that over at +2 in a minute. Okay, so this is a lot of work. Here's what you're supposed to do. You're supposed to imagine that you're plugging in numbers like -2.1 or -2.01 or -2.001, you see? And then on this one, you're supposed to imagine plugging in like -1.9 or -1.99 or -1.999. Okay, now you're not going to use a calculator. You're just going to sort of estimate this. So on this first one, if you plug in a -2.1 or a -2.01 or a -2.001 on top, it's going to be a negative, obviously. So you'll have like -2.1 on top or -2.01 on top or -2.001 on top. Right? Sorry, it's messy. I'll rewrite that last one. The bottom, though, has 2 parentheses. So I suggest you use the factored form to do this kind of thing. When you plug in -2.1, this is just going to be -0.1, and this is just going to be -4.1. See? This is going to be -0.01. I'll do that in red. -0.01 and -4.01. -4.01. And the same thing for the last one. The last one's going to be -0.001 and then in the other parentheses, -4.001. Okay. My point is this. The tops don't change much. I mean, they get closer to -2. The bottom has 2 things. You've got the -4, -4.01, -4.001. Those are all roughly -4. But see that red number on the bottom? That thing's shrinking. See it? -0.1, -0.01, -0.001. When you have a -0.1 on the bottom, it really means multiply by -10. When you have -0.01 on the bottom, it means really multiply by -100. And then -0.001 really means, since it's on the bottom, it means multiply by -1,000. But 2.1 over 4.1, 2.01 over 4.01, 2.01 over 4.01, those are all roughly 1/2. But the bottom is exploding because the bottom's causing things to explode. This is going to go to -50. this guy's full. Right here. The negative 0.1, negative 0.01, negative 0.001 there on the bottom. You see him? Okay, so we believe that this is going to go to negative infinity. Now, how much of that did I really need to write, and how much of it could I have just done in my head? Turns out you can actually do all of that in your head once you get practiced at it. You just have to realize that when you plug in numbers near negative 2, that little term on the bottom is going to go quickly to 0. And then what's going to happen is the fraction is going to explode. It will explode in one direction or the other, either up or down. In this case, down. Because it's 3 negatives when we plug these in. So I'm going to actually do the negative 1.9, negative 1.99, negative 1.999 a lot faster. Okay? First of all, I'm not going to write every little thing I think. I'm just kind of reason through this. The top is going to be negative, right? Because it says x. So I'm going to plug in negative 1.9 or some negative number here, negative 2. So I'm going to plug in negative 9, negative number on top. That top's going to be negative. This x plus 2 now, it's going to be extremely close to 0 right here. So this is going to basically go to 0 plus. 0 plus. Because, for example, if you plug in negative 1.9, you're going to get 0.1. If you plug in negative 1.99, that first parenthesis is going to give you 0.01. If you plug in negative 1.999, you're going to get 0.001 here. In other words, that thing's going to 0 from the right. The other part, well, that's just going to like, you know, negative 3.9, negative 3.99, negative 3.999. This thing's like going to negative 4 from the left or something. But what's going to happen is you have basically negative over positive times negative. So what is the net result when you divide a negative over a negative times a positive? The net result's positive, so we're just going to get infinity for this. Listen, you already know it's a VA, right? You already know it's infinity or negative infinity. We're just trying to decide which. Does that make sense? We already know it. This is either infinity or negative. It's a vertical asymptote, folks. Okay. So it turns out that the answers are negative infinity and infinity. So graphically, of course, what that means is, here's a real rough sketch. There's an asymptote at negative 2. There's an asymptote at positive 2. So far, we've studied the left and right side of negative 2, and we have learned this. This side shoots down, and this side shoots up. That's what we've learned so far. Those are our two answers. Okay, now it's time to study the other asymptote, right? So you're going to repeat this, only now, don't erase, but just continue working. You're going to be going to positive 2 from left and right, and you can do this really almost entirely in your head, like I said. So we're going to try to abbreviate our work even more. So we're going to be going to 2 from the left. Always use the factored form. It's so much easier to process in your brain. Okay, remember what this means. Numbers like sorry, that's not true. Numbers like 1.9, 1.99, 1.999. Okay, so the top is going to be positive. The bottom is going to be 1.9 plus 2, 1.99 plus 2, 1.999 plus 2. This is getting closer to 4 from the left, so it's positive. And then this guy, the x minus 2, see that guy? He's going to go to 0. Now, is he going to be positive or negative? So think of it as 1.9 minus 2, 1.99 minus 2, 1.999 minus 2. They're all going to 0, but are they negative numbers or positive numbers? Technically they're negatives. Right. 1.9 minus 2 is negative 0.1, for example. So this comes out negative, and we know it's an infinity. See? Okay. The last one I need to calculate is 2 from the right. By the way, everybody hates what I'm doing here, so if you're feeling like that's really annoying, don't worry, you're in good company. I feel the same way about it. The top, you're plugging in numbers like 2.001, you know, real tiny positive and greater than 2 numbers. Okay, so the top's going to be positive. I think this is going to be positive, and this is going to be positive. In fact, everything's positive because the top's positive because it's just x. This is going to be like 4.001. This is going to be like 0.001. Everything's positive here. And this is going to explode to infinity. You will get to the point where you only have to do one of these, not both, because you can predict the other ones. I'll show you how to do that in about 10 minutes. And you'll get to the point where you don't even have to write these positive things. You can actually think of it. Okay, you'll get pretty fast at it after tonight's worksheet. Okay, but tonight's worksheet, I think you probably need to kind of show some work, scribbles on the side or whatever. Okay, we just learned something about our asymptote over at x equals 2. We learned that the left side goes down and the right side goes up again. So I wouldn't be surprised if when I graph this on my calculator, the graph looks something like this blue curve. Okay? That's a pretty big jump to try to sketch the whole curve based on asymptote behavior only, but it's a logical guess. It's like a good first draft, and then we tidy it up later. It might have some holes in it. Actually, we know it doesn't. Never mind. We've already studied. There's no holes. So yeah, it's got to be nice and continuous for those 3 branches. Okay, so that's actually a pretty good graph. Are there any turning points? We don't know. We don't know. Not from this analysis. Okay, that's a hard bit of work, right? Like, that's a lot of work. Okay, let's look at our next one, which has a hole and an asymptote. So let me give myself a little more space here. Okay, so this one factors into x plus 3, x minus 3, and the bottom into x plus 7 times x minus 3. I think I factored it for you yesterday. And you can see that the x minus 3 just cancels out. Okay, so that means actually that there is a hole at x equals 3. And if you want to study the behavior of the graph on both sides of the hole, just do a limit. Check the 2 drivers as they drive towards the point x equals 3. So you just basically go LIM x goes to 3 and use the simplified reduced fraction. You just get 6/10, so that's 3/5. Okay, so we found the hole and the behavior on both sides of the hole. One limit gets both behaviors. Real quick, by the way, that just means that the hole is at 3, 3/5. Hole at 3/3 is what it means. Okay, let's look at asymptotes. Where is my vertical asymptote on this problem? You can answer as a class. It's at x equals -7, right? So fortunately, there's only one asymptote because that was a real pain last time. We had 2 of them, remember? Okay, so let's just draw a quick scenario. Here's x equals -7. There's this vertical asymptote here. If you do LIM x goes to -7 from the left, and just use the simplified function. I think you can do this one in your head. It's actually a lot easier than the last one. The top is going to go to about -4, because you're basically plugging in -7. Both numbers close to it. But the bottom is going to go to 0, naturally, because you're plugging in -7. Actually, you're plugging in -7.01. Okay, so the top is going to basically be negative, roughly around 4, -4. I'll just put negative. And then the bottom is going to cause it to explode. It's going to go in one direction or the other. If you plug in -7.1, for example, it's going to be -7.1 plus 7, which is negative. Plug in -7.01, it's -7.01 plus 7. So it's getting close to 0, but it's coming from the negative side. So this is also negative. So we just learned that this graph shoots up to where? Positive infinity, right. Okay, so we just learned our arrowhead on this side goes this way. Now last time, on the last problem, we noticed that the behavior seems to always be the opposite on the other side, right? Turns out that's actually a pretty good rule of thumb. You could actually pretty much take that to the bank. I'll show you in a minute when it won't be opposite, but in this problem it's also opposite. So we'll save the time. We're going to assume that the other arrowhead goes down. Okay? And I'll show you why in about 30 seconds, so stay tuned here. Okay, so we would write that, of course, as LIM x goes to -7 from the right. is negative infinity. So we always write our limits. They are sort of a capture. They're like you capturing the facts and writing them mathematically for me to read. So the reader could actually take these red statements and start drawing the graph, is the idea. Okay, now, when will it ever be the two arrowheads both go up or the two arrowheads both go down? That can happen, and it happens on our next example. Maybe you can already see why. Does anyone want to make a conjecture why on this next one we're going to get the same behavior on both sides of the asymptote? Anyone care to take a guess? I'll pause the recording. So this problem has another takeaway that the others didn't. So we're going to factor the top, x plus 1, x minus 1. The bottom, I already factored it for you because I thought it was kind of awkward to factor a cubic beginning of pre-calc. You can see that your x minus 1 cancels. We know what that means now. We know that that's a whole at x equals 1. To study the behavior, just do a limit at 1. And I worked this out earlier. I got 1/8 because you get 2 over 16 basically when you plug in by direct substitution. So 1/8. So your whole is at 1, 1/8, you could say. Or the behavior near the whole is 1/8 behavior. Okay, now the vertical asymptote. Where's our vertical asymptote at, class? -3, right. So the vertical asymptote is -3. If you do LIM, x goes to -3 from the left of x plus 1 over x plus 3 squared. It's actually a really easy one to analyze. Imagine plugging in -3.01. The top would be, you're supposed to say negative or positive. The top would be, imagine plugging in -3.01 on top. At 1. The top is negative. Good. The bottom's close to 0, obviously, always. And positive or negative? Positive. Why? It's squared. Yeah, who cares if it's coming to 0 from the right or the left? It's squared. The behavior is going to be, actually, it's going to approach 0 really fast. Like, because 0.01 squared is 0.001. Negative 0.01 squared is negative or it's also positive 0.001. In other words, it's going to approach 0 extremely quickly from the right because you're squaring. That's the idea. Okay, so it's definitely negative over positive. What's our conclusion? Negative infinity is our conclusion, right? Negative infinity. We always answer with an infinity on these. Okay? Probably shouldn't draw too much arrow. Just draw a little bit going down there. And the right side is actually going to be exactly the same. Because if you change from plugging in numbers like -3.01 to numbers like -2.99, the top is still negative and the bottom is still positive because it's squared. So the right side also goes down to negative infinity. And this is how the asymptote behavior works when you have an even multiplicity on the asymptote term. So it's actually getting easier as we kind of see more clues, and we're not plugging in numbers all the time. But you are kind of supposed to do all this in your head or with a little bit of scratch paper. All right. So much for vertical asymptotes and hulls. Now let's look at horizontal asymptotes and oblique asymptotes. So there's a word here, proper. I want to remind you, you learned it, I think, in 5th grade, maybe 6th grade. Proper fraction versus an improper fraction. This word shows up this year quite a bit. So a proper fraction in math is like 5/6 or 3/4 or 9/10. Okay? An improper fraction is like 5/5, 4/4, 11/11, or even worse, 12/11. Okay? Now, the reason these are not proper fractions is not because they're dressed incorrectly or they've somehow been improper by burping at the table, or that kind of like negative connotation improper. It's just technically they're not fractions. If you think about it, like 5/6 is truly a fraction of a whole. It's a part of a numbers anymore. Some of you yesterday on the quiz found a vertex at 1/4, negative 63 eighths. And some of you insisted on writing negative 1/4 and negative 7 7/8. But see, in high school, you were taught that when two numbers are near each other and there's no symbol in between, it means to multiply. Right? But that's not what 7 7/8 means. It doesn't mean 7 times 7/8. It means 7 plus 7/8, technically is what it means. So we don't use mixed numbers. Please stop using them. Okay? Or maybe on my vertex on that last quiz, number 2, the vertex was negative 57/8. Some of you wrote negative 7 1/8. Okay, don't use mixed numbers at all. Improper fractions are perfectly acceptable. They're just not truly fractions, that's all. All right, now, if you have a proper degree polynomial, that means like the top is x squared, the bottom is x cubed, or the top is x to the 4th, the bottom is x to the 5th, or the top is x, the bottom is x cubed. If the top truly has less power than the bottom, then that's called a proper rational function. So it's exactly the same thing as the numbers, except they're not coefficients, they're powers. So these are proper rational functions, and every single time y equals 0 is going to be your horizontal asymptote. Okay? This second sentence talks about what you do if the fraction's not proper. Like if you have y equals x squared plus 5 over x squared minus 3. We've already done problems like this. This one's technically not a proper fraction, but it still has a horizontal asymptote. This one here is not a proper fraction, x cubed plus 5 over x squared minus 3. This one's not a proper fraction, and it doesn't have a horizontal asymptote. So what we need to do is talk about these kinds of situations. So the first sentence is just saying if you have higher degrees on the bottom, it's automatically going to go to 0 when x gets big. Automatically going to go to 0. And therefore y equals 0 is a horizontal asymptote. And on simple problems like these, it's actually in both directions. We'll go to 0 both directions. On this one and this one, these are two different scenarios with two different results. Both are improper fractions. And this down here tells you how to handle these kinds of problems. And you're welcome to read it later, but I'm not going to get too carried away because I can teach you by example too. Basically, the bottom line is you're going to try to divide and you're going to see what you get as a result. Then you're going to let x get big. So let's look at these 3 examples here. It's this next page. 4 examples, excuse me. Okay, the instructions say, determine the horizontal or oblique asymptotes for the given rational function. All right, so the first one, you'll notice it's bottom heavy. The x on top is first degree. The x squared on the bottom is second degree. So this is proper. It's proper. And the answer is there's a horizontal asymptote at y equals 0 every time. Now to show the work, you could just write LIM, x goes to infinity, x minus 12 over 4x squared plus x plus 1. Circle your end behavior models. And this reduces to LIM, x goes to infinity, 1/4. And as far as 1/4 is concerned, 1/4 will always be 1/4, no matter what you make x. So this just comes out to 1/4. Mr. Short's messed up. It's 1/4x, my bad. It's 1/4x, which is going to become 0 when x is large. So 1/4 million, 1/4 billion, 1/4 trillion. Sorry, there's an extra x down there. I was getting ahead of myself with my number 2. Okay, so this one's going to go to 0. I don't know if you need to show work on that, but I would like to at least write the statement. The limit as x goes to infinity is 0. Okay? All right. So those are actually really easy. The proper ones always go to 0. The only time those could ever possibly be difficult is if they purposely try to mess with you and they put x minus 12 here, and then on the bottom they put like 40,000 minus 2x squared. And so your eyes are looking at that 40,000, you're like, oh, that's the biggest term on the bottom. But it is not. You want to circle your end behavior models before you start. So that's your biggest, most powerful term on top. Obviously, x is much bigger than 12 when you go big. And on the bottom, technically, negative 2x squared is way bigger than 40,000 if x is like 3,000. Okay? So don't be fooled. Just look for the highest degree term. Don't pay attention to coefficients at all. So those are pretty easy. But it's going to go to 0 if it's bottom heavy. Next one, this one is not bottom heavy, nor is it top heavy. It's just a kind of balance of power here. You've got x squared on top, 4x squared on the bottom. This one's going to go to 1/4. Okay, so you could just basically write y goes to 1/4. It's because the degrees are even, or not even, but the same. There's no winner as to who's going to win. So they both win. So you just basically go LIM of 1/4. And that's just 1/4. Okay, so that's how you show your work. This next one, though, we have to be careful. This work gets pretty hard. Because the fraction is improper, let me erase. Okay. Because it's improper, you're going to want to first do long division. Okay, so give yourself plenty of space here. Maybe you even want to do this one on the back, or even the, I think you have another page that is blank, right, on the back. You might want to write a note, see back of packet for this one. Okay, so just like it's easier to understand a number like 7/6 by first thinking of it as 1 plus 1/6, right? It might be nice to sort of rewrite this function. It'll make it so much easier to understand it. Okay, so I'm going to go ahead and do long division. X cubed minus x squared plus 1 goes into 3x to the 4th plus 0x cubed, don't forget your placeholders when you do long division, minus x squared plus 0x plus 0. At least on the inside of your division, you want to put in placeholders. You can also put in placeholders if something's missing on the outside, but it's not quite as important. Placeholders are very, very important, okay? Especially on the inside is what I'm saying. Okay, so you guys remember how to do this? First you ask, what do you multiply x cubed by to get 3x to the 4th? So you only look at the NB-Hidden model. You would need to multiply by 3x, right? Okay, then you take that and you multiply it with all three of these. And you record your result on the next row. So it looks like this. 3x to the 4th minus 3x cubed. There are no x squareds, so put plus 0x squared, and then plus 3x. Okay? So with our placeholders in there, I'm changing them to red. With the placeholders in there, it's really easy to line everything up. And in long division, remember, we subtract. So now we subtract. Or you can just change all the signs and add. But anyway, you're going to get 0 for the first term every time. You're going to get 0 minus negative 3x cubed, so that's 3x cubed. Negative x squared, take away nothing, so negative x squared. 0x, take away 3x. And then you're supposed to drop this down, even though it's a 0. And that's the first loop in the division algorithm. Now you start all over again, right? You ask yourself, how many times does x cubed go into 3x cubed? Or what do you multiply x cubed by to get 3x cubed? What's the answer to that question? Multiply by 3 to get 3x cubed, right. So you put a plus 3 up here. And then you distribute. So this gets distributed to all three of these. And you record your results underneath. 3x cubed minus 3x squared plus 3. So I'm going to write plus 0x plus 3. This is long division, so we subtract. 3x cubed minus 3x cubed is nothing. Negative x squared, take away negative 3x squared. In other words, negative x squared, add 3x squared. So that's 2x squared. Negative 3x, take away nothing. That's negative 3x. 0, take away 3. That's minus 3. Okay, so here's what we just learned. Since we can no longer divide x cubed into this first term, this is now our remainder down here at the bottom. So what we've just discovered is that this function can be written as 3x plus 3, watch close, plus garbage over the original divisor. Now, if you let x go big, in other words, if you do a limit, this term is going to vanish because it's bottom heavy. And we learn that we're going to get y equals 3x plus 3 as an asymptote line. Y equals 3x plus 3. Here's what it means graphically. Your graph will in some way approach the line 3x plus 3 on both ends. So there's going to be one arrowhead that follows the line 3x plus 3 down here across the trace somewhere. Then there's going to be one arrowhead that follows the line 3x plus 3 over here. It's either going to come from above or from below. We're not quite sure yet. But this is our asymptote line that dictates the function. It's the role model for this function. Obviously that's awkward. Your worksheet has one of these on there, so make sure you do your long division properly. Just throw away the remainder term, basically.